Okay, so right now we're going to do the proof that IIA is not only an implication, but is also all the implications possible. Are all, basically captures all the possible implications of the logit model. So therefore, the following are equivalent. The stochastic choice data satisfies loose IIA and also admits a logit representation. So we already proved that if you're logit, then you have to satisfy IIA. Okay, that was done before. It's just this ratio. So now I want to prove the other way, right? So 2 is that this stochastic choice rule, basically, sorry, this is 1 implies 2, satisfies all IIA, and this of course implies that you're logit. So what I have to do is I have to do a constructive proof. So I'm going to build the average utilities. So how do I do it? Well, for simplicity, I'm going to define that this exponential of the average utility with this simpler notation for any alternative x on the choice set is going to be called W of x. So W of x is the exponential of the average utility for simplicity. Okay, so I don't have to write exponential every time. And I'm going to define it as the probability of x on the grand choice set x. Because I have all complete data, I observe these objects, and this is positive, a positive number, a strictly positive number, in fact. And then what remains to be proved is that these W's x as generated for all x generate the data in the logit rule. Okay, so I have to verify basically that any probability for any x in a particular choice set A has to be generated as this logit rule. So let's use IIA to prove that. So by definition, IIA means that if I take basically this x here, right, and I divide this probability of A for x star, which is another alternative that is fixed, and I divide this object here, this has to be equal, this ratio has to be equal to the probability of x without a star divided by the probability of x star in the grand choice set x. And fixing the condition on A, I have the division of x without the star over x with a star, right? So I rearrange terms under positivity, and then I kick this probability here in the numerator, and so this just calls for by IIA. Everyone's on the same page, so this is just a rearranging of IIA. Now, what I want to show eventually is that the probability of this x condition on A is equal to this division of the exponential of the average utility by the sum of the mean utilities in the menu. Okay, so how do I do it? Well, notice that this quantity here, by definition, is just the Wx. And this quantity here in the denominator is just the Wx prime. Okay, now take this expression, and this holds for all x, right? Okay, so now I'm going to, so you don't get confused, I'm going to take a summation of these functions above over the whole set. So I'm just changing the argument that is irrelevant, right? Because I know this for all elements in the capital A. So now the summation over all elements in the menu A of this rule above is the summation of the argument on the right-hand side. So now notice that this term here does not depend on y. It depends on x star, which is fixed. So this is a common factor of this summation, right? So this common factor can go outside, okay? And now the only thing that remains is that you have the summation over the wy. And what is this? This is the summation of probabilities for all set. By definition, this is equal to 1, okay? So now if I divide this, it's going to be that this thing here is equal to 1 over the summation over the average utilities. So replacing back to the original definition, I verify that the probability of x in the condition of the menu A is equal to this logit rule for the dx. So everyone agrees? So I have proven that IAA under positivity implies logit. And of course, the other way around is the same. So this is the characterization of this model completely. Now, are you happy with this? Well, not yet, right? Because we talk about random utility very general, and now we're doing logit. So logit is like a Cobb-Douglas, so it's still not great. So now let's go back and let's study the general model. So take a choice set X and consider now a general probability space. So this is kind of back to metrics, a little bit probability. So you have here the state space with a sigma algebra and then a probability measure, right? And this is a sigma algebra measurable random utility function that is mapping basically these states to basically values functions, right? So this is a random function. So in other words, for each omega, you have a utility function. So it's not just utility numbers, it's a utility function. So therefore, this is a random utility, okay? So everyone understands what I'm doing? So examples of random utility. So for instance, imagine a Cobb-Douglas that now the parameter alpha is random, right? So let me do this, introduce here an example. Random Cobb-Douglas, right? So imagine here that I have a utility over basically two goods equal to x alpha y 1 minus alpha, and alpha is distributed, right, with basically, because this has to be 0 and 1, with a uniform between 0 and 1. Okay, so this is an example of random utility. Okay, so what is the state space here is the alpha, right? So for this case, omega is equal to the 0, 1 into, okay, and so on. What is the sigma algebra is the Borel sets, right? And then what is the measure is the uniform measure. Got it? So this is a random Cobb-Douglas utility. You can imagine others. Now, let's define the event in which an agent chooses alternative x from A. And this is going to be called Cx comma A. And this is just basically the set of these omegas and capital omega, such that for the realization of the random utility, which is our utility function, x has the highest utility in the menu, okay, strictly. So what is this object here? Is an event. So therefore, if you want, you can think of an indicator function. Whenever x is picked out of A, because it maximizes the realized utility, then this is 1, okay? So what is a random utility rule? So rho, the stochastic choice dataset that we defined before, which is this collection of a stochastic choice dataset over menus, has a random utility representation if there exists a random utility, right? Which is this bold U, and such that rho of the conditional on the menu A of alternative X is the probability of this event, okay? Is the probability that of the measure over all these state spaces, such that this is the top alternative. So according to the Cobb-Douglas, it will be the measure of the alphas under which the particular alternative X is being maximized, is the maximum, sorry. Do you understand? So everyone's on the same page here. This is important. So random utility, in other words, is just telling you the measure of this random utility under which the alternative X is the maximum in the menu A. Okay. Now, random utility again, you have here the two interpretations, right? It can be an individual stochastic choice data set, or it can be a population interpretation. So for instance, in the Cobb-Douglas example, alpha can be heterogeneity across agents, right? but it can also be instability of preferences for an individual, right? Shocks to preference. So any interpretation, I don't care. Choices are not random. Now they are choices are not deterministic. Now they're random, and I can only predict this probability of choice. I can no longer predict the deterministic choice. Okay. So alternatively, another way to write it is basically the measure over the utilities conditional on this utility being greater for V for all V, right? So this is basically another way to write the random utility. But whatever you prefer, I like this one, of course, with the events, it's clearer. And with this model, we're going to study in a bit in full generality. And at this stage, I want to ask you the following thing. So we know from deterministic choice that choice correspondence has to satisfy the strong axiom, choice function has to satisfy the strong axiom of revealed preferences in this rich data set, right? So it has to be that a stochastic choice data set has some sort of testable implications, right? So you have to have, in fact, something that is weaker than the IIA that has to do with GARP, right, in some way. So we haven't obtained the analogous of the strong axiom or the generalized axiom for random utility, okay? So this is still unknown. So I'm gonna get there eventually, but I'm going to present you before a special case of a model of random utility that is a generalization of the expected utility model that we already studied. And this is called the random expected utility model, okay? So let's go back to our previous chapter. So we have choice under risk. Set is the final set of prices, money. What is the choice set? Is the lotteries over money. And then we have typical items here, P, Q, and R. Okay, these are lotteries. So now, what is a random expected utility model? A random expected utility model is such that the realization of the random utility is, in fact, expected utility, right? So instead of having random big U, I have a small random U. So random Bernoulli. And the Bernoulli is now a random mapping that is over money, okay? So now you have random attitudes towards risk. So before I present you with the axioms, I'm going to give you this example that I should have put it before. So random CR array, okay? So everyone knows the CR array utility from Bernoulli utility, right? Now imagine that you have now this randomness on the risk aversion, okay? This is distributed with some probability F, okay? Maybe uniform, okay? Maybe normal, maybe a Gaussian, okay? And now what is the probability then of choosing lottery P in menu A of lotteries? Is basically the probability over events such that the expected utility according to this omega is greater than the expected utility of Q for all Q different than P in the menu. So here we're basically seeing the probability of risk aversion parameters, right, that make P the maximum. Got it? So now this model basically means that in the interpretation of an individual, that individuals are changing the risk aversion at random, okay? So some days you want to take more risks, some other days you want to take less risks. That's an interpretation that's kind of cute, but I don't think it's great. The best interpretation is the cross-sectional interpretation. So you have a collection of individuals in a cross-section, and all of them are CRA, and all of them are endowed with a realization of a risk aversion parameter, right? So of course, in a population, you have a lot of people that are risk averse, some people that are risk neutral, some people that are risk lovers. Got it? And this distribution is going to be the F distribution. Got it? So now, okay, so what are the implications of, or the axioms of this model? This model is, of course, very different from IIA, from logic. And now I want you to understand what are the axioms. So what is your first expectation of this model? So this model should have some sort of axiom that looks like the independence axiom, right? Like for expected utility. Okay? So, and in fact, I'm going to do that next. So define menu expansion. So take an original menu of or lotteries, and then this operation, which is alpha of the menu plus 1 minus alpha q, basically means is defined as the collection of all alternatives that are the mixtures of p in A mixed with q. Got it? So I'm taking the set of lotteries, and then I'm doing compound lotteries with q, and I create a new menu, which is the menu of compound lotteries. Got it? And I have only one mixing object, which is the q. So it turns out that one implication of this model, which is the main implication, is called linearity. And for any alpha in 0, 1 open, for any two lotteries P and Q, we have that the probability of picking P, conditional menu A of lotteries, is equal to the probability of choosing the mix of P with Q, according to mixing parameter alpha, in the menu expanded menu alpha A 1 minus alpha Q is the same. Okay? So why is that? So we're going to understand it in a second, but my claim now is that expected utility implies this property. So let's go to our proof. So I'm going to have this result that I'm going to read by parts. So the theorem tells you that the expected utility representation, which I don't know why it moved, satisfies the following conditions. One of them being linearity, the axiom I just defined. I'm going to go to the other axioms later. So we're going to show linearity holds. So think of this random Bernoulli utility. And now this means that the probability of choosing P in menu A is equal to the probability of the event of choosing P in A, right? And this is equal by the property that they are expected utility to the probability of the event, basically alpha P plus 1 minus alpha Q in the expanded menu, because of the expected utility structure, right? This is from the previous chapter. So what happens is that for every realization of omega, we have the expected utility behavior happening, right? So almost surely, these events are the same, so therefore the probability over them is the same. So that means that this probability over the expanded menu with Q is equal to the probability of picking the compound lottery alpha P with alpha 1 minus alpha Q is the same as the probability of choosing P in the original menu. So everyone understands this? So this is the stochastic counterpart of the previous chapter. Okay, now that was easy. Now I'm going to give you something that is less easy, and we're going to spend the last 5 minutes doing this. You are going to do this. So I claim that this model, random expected utility, implies the following axiom. So take an alternative that lives in A, but also in B, and turns out that B is a superset of A. So B has more alternatives than A, right? For simplicity, imagine that it has strictly one more alternative. So V is the original A plus a new alternative, okay? Then I'm going to claim that the probability of choosing alternative X that is in both menus when the set is smaller is greater than the probability of X when the set is bigger. So, and in particular, when the set is strictly bigger, the inequality is going to be strict, okay? So what I'm telling you is that as the menu grows larger, the probability of X decreases, right? So can anyone tell me why? So you have basically 3 minutes, but basically using the logic of random utility.
Well, maybe if you're choosing this X, like the utility is not really going to change regardless of what the pool of stuff that you have. And if your pool just becomes bigger, then your probability of choosing is smaller.
Great, great, it's perfect, right? So you fix the alternative, right? And it's going to be maximum for a subset of utilities, right? Of omegas, if you want. So as you throw more alternatives in, right? The likelihood of this happening is going to shrink weekly, right? Because the more alternatives you throw in, is likely that one of these omegas under which this was the top now is not going to be longer in that set, right? So some of them are going to be, the new alternative is going to be the top of some of the utilities in that set. So it's going to shrink the set. And yeah, so it turns out that regularity is an implication of general random utility. So Eduardo didn't use expected utility because you don't need to, right? So the expected part goes in the linearity part. This is just an implication of general random utility, okay? So Eduardo just found the first implication of random utility. Now, turns out that for general random utility, so in other words, remember the weak axiom? Regularity is basically the weak axiom for stochastic choice, okay? So now, of course, you are still missing the version of the generalized axiom of real preference order. So what is that? That turns out to be very hard, so it's not as nice as regularity. We're going to see it next class. But for the special model that we studied today, for the model of random expected utility, you don't need to add this GARP version, right? So you just have regularity, which is the work version, and you add to it the linearity, okay? So now let's go back, and I'm gonna tell you the other axiom that you need for this model, so extremeness. So imagine that your choice set is a polygon, right? And now remember that expected utility are lines, right? So they're going to be maximized in some extreme point. So the extreme of this set A are going to be this boundary of these polytopes. Now, the probability of choosing some element in this set of extreme points is going to be 1 because of the linearity, okay? So this is a rather technical axiom. I don't think it's that important, but it's needed. So therefore, this famous result by Gould and Persendorfer says that the stochastic choice dataset has a random expected utility representation, even only if, right? If it satisfies regularity with Eduardo's found linearity, extremeness, and continuity that I'm not going to define here because this continuity is very technical and I don't care. So now we have, we check linearity already, and we of course are going to check, Eduardo already checked regularity. Extremeness, this is the graphical proof of why it holds. Now the other way around, the proof is beyond the scope of the class, so I'm not going to do it. So I just proved necessity. So now we just have testable implications. Now, I want you to realize the following thing, and let's go back to this random zero array in the last minute, and is that this model actually is very powerful, right? Because now if you want to study what is the fraction of people choosing a probability P when the choice set is A, this is going to be an integral, right? Over types. So now types are risk aversions, okay? So this is an average over risk preferences. So this model is very different from the previous one because the previous one has a mean utility, right? And then adds shocks to it. Instead, this model has an average parameter and then has shocks to the parameter. So for instance, one way to write this would be that the parameter of omega here, the risk, right, is equal to some mean parameter plus a shock, okay? Just epsilon, okay? So this is a different model from before because instead of shocking the mean utility, we're shocking the mean parameter, okay? So there is some average risk aversion and then I'm shocking the risk aversion, okay? So this is a different kind of model. So these two models are both of them special cases of random utility, but both of them capture very different behavior. The first one, the loose model, is shocking mean utility. This one is shocking mean risk aversion, okay? So this is the new generation of models, right? So people are using this model way more. So now basically you can think of all models that you have seen in your life, like Cobb-Douglas, CES, CRAs, CARAs, and whatever, right? And all of them, now you can think of the stochastic version of it, okay? And now think about the Alep paradox. So the Alep paradox, right, was the phenomenon that you have a sample of individuals, so a pool of subjects, and some of them choose this inconsistent choice that L1 over L1 prime, and then you have the flip, right, to L2, L2 prime. Now, question. So can you use random expected to explain this? So the answer should be obvious. The answer is yes, right? So random expected utility, of course, allows for a lay behavior in population, right? So this is not for an individual. For individual, you cannot do anything because it's only 2 draws, right? But if you have a fraction of individuals that are behaving in contrast with a leg, this is not a problem for this kind of model, right? So there may be some, because this, you're allowed to change your preferences, right? So at some point you may have a higher draw of risk aversion, then you may become very risk lower, right? So you may be flipping, okay? So this allows for instability of preferences. So this puts in new light a lot of phenomena and behavior, right? So this model actually, I think, is better than these models of loss aversion and so on. So yeah. So in this new generation of models, what we're basically understanding is shocks to random parameters. So I'm going to stop there, and then I'm going to take questions.